Hello everyone, this is Astarag, and in this video we'll be going through JAX ML part 3, and we'll be going through the exercises, the remaining exercises. In part 1 we discussed about everything about how sharded matrix multiplication works, and there we solved till question number 4 from the exercise. But in this video we'll be going through each question from question 5, and and these are really important questions, so I will advise you to start with a pen and paper and then start solving each of them. Let's start with question number 5. Let's read the question. Let's say I want to do matmul between b comma d and d comma f, and d is the contracting dimension. We get b comma f on a TPU v4 v5p architecture, and we want to do it in the lowest possible latency. Before jumping into solving the question, let's first revise what was the communication in all gather and reduce scatter and all reduce. So in last lecture we discussed three main communication patterns: all gather, reduce scatter, and all reduce. And we also saw that all reduce is equal to uh, reduce scatter plus all gather. So if we look at the communication for all gather, it will be something like, suppose you have a array of size v, and you have this is array size, and x is your number of devices. Then you have something like this, where each device has vyx array vyx, and you will be transferring data through them in a bidirectional fashion between them, and because of the wraparound link it is connected. And so the total time taken would be you are sending here v data vyx, and also you will be receiving vyx. So every time there is total bandwidth of 2 vyx, and the time taken is 2 vyx and into number of hops. So number of hops is equal to for given number of devices, uh, how how long does it take from one data to get transferred to all the devices. uh, as it is bidirectional, so it will take x by 2, and this will give us value of uh, one more factor I was missing was 1 by w is the bandwidth, and it is v by w. So this is the time taken for all gather and reduce scatter, because both of this communicate the same information through the GPUs, through the devices. It's just like all gather keeps those extra arrays, but reduce scatter only keeps the array that it needs for that device. So all reduce is twice as expensive as all gather or reduce scatter. So if we now try to solve this question, we have 4 patterns here, and 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 our device is TPU v5p architecture, which is 4 cross 4 cross 4. So it's a 4 cross 4 cross 4 uh, mesh shape, and we'll be sharding our arrays. So we have this to multiply, and we'll be sharding across this device, and we'll be, for different type of combinations, we'll be seeing how much we need to communicate. We will jump back to one of the visualization, and in this visualization we will so this is question number 5. So all this code would be uh, available to you, so you can go through and visualize. So the first pattern that we will see is this pattern I, where we shard the first dimension across the three axes. If you remember our TPU V4 V5P architecture, where 4 comma 4 comma 4, which was a three axis, which had three axes. So here we are going to shard the first axis along the three axes, and then we will do the matrix multiplication, and after doing the matrix multiplication we'll do an all gather. um, so let's discuss what's the amount of computation uh, computation you need, which is the total flops, and the communication time. So you have to do these operations where I x y z comma j, and you have b, sorry, I will write a b here, and it will be d here, and it will be b matrix would be d comma f. So you will do a matrix multiplication, and you will get a matrix of c for, and this would be for each device, b x y z comma f. And now you want to do an all gather along these three axes to get back, so that every so this matrix is repeated across all the devices. So to do that, I will first add a new page, and page. To do that, so we will be doing flops here. We'll be calculating first flops here in this operation, and then we'll be calculating the num uh, communication time here, comms time here. So if I have to calculate the flops, remember, like this dimension or like sorry, this dimension is sharded across the four axes. So um, so this b in the matrix A, the b part, the b row is sharded across the three axes. So it will be of value b by 4, because it is sharded across four across the four dimension, like here x, y, and z. It is sharded across four of them, and you have four. And now, as all of these are sharded, so for each device you only have a partial b, so you will be only doing operation for that shard in that device. So for this device you would only have, say, b by 4 comma d and d comma f. So you will be only doing operations for uh, b by 4, d by 4, because the rest of the part in a device is not essential, and then f by 4. You will be doing all these operations, and as we have discussed in matrix multiplications, um, it is two times of the or if the shapes of the array. So you will have a factor of 2 here, and there seems okay. This is a mistake actually. So this is not correct. So let me rehash. So B is sharded across the axis. So B is sharded across X, B is sharded across Y, and B is sharded across Z. So you have 4 by 4, 4 comma 4 comma 4 in your sharded B. D and F, they are actually being done operations on. Like so if you remember this from our uh, previous lecture, this is comes under case 1, where the non-contacting dimension, here the non-contacting dimension is D, is not sharded, but this dimension is sharded. So you need to do the full operations here. So this will be B by 4, B by 4 comma 4 comma 4 into D into F. So this is the total number of flops that you need to do. And uh, when you are doing all gather, during all gather you will, as we discussed here, it is given by V by W, and V is the size of the array after doing matrix multiplication. So after doing matrix multiplication, your size of the array is this: C, B, X, Y, Z, F. So your size of the array is this. So you will be doing matrix multiplication on that only. You will be doing communication on this only. So it is 2, uh, and the total size is B, F. This is the total size of the array divided by, uh, so you have 3 axes here, and you will be doing all gather across the 3 axes. So it will be 3 into the bandwidth. And the bandwidth for, if I go back to how to think about TPUs, previous part, I go to this where they, sorry, how to think about TPUs. I go here, we are talking about V5P architecture. uh, uh, you can see like the bandwidth here is 9E10. So so this is the uh, bandwidth that you have uh, in bidirectional. Sorry, this is the bandwidth for bidirectional. And if I take that, so I will get the bandwidth here is 18 to the power 11. So this 3 comes from that you have sharded across 3 axes. All gather across the 3 axes is can happen simultaneously. Like you don't have to wait to for one axis to complete, and then you will move on to next axis. So all these 3 things happen parallelly, and then you have a bidirectional bandwidth of 1.8 into e to the power 11 that we saw now. So this is your all gather operation, and this is the total number of flops. And as you have sharded your B, so you have B 4 into 4 into 4. So this is the first case where the first axis is sharded. Uh, first axis is sharded. Coming to the second case, we have this, where the second case is A, B, comma D, and so let me just write. And here this one is sharded, X, Y, Z. So this F is sharded. Let me just write it better, X, Y, Z. So this one is sharded. So we'll do our mesh again. We have 4 axes, and we are gonna shard F across all these 4 axes. X, this is Y, and this is Z. We are going to shard f across this three axes. And if you see here, this is very similar to what we have here. So uh, the calculation would be very similar. So the flops here, it would be 2 into b into d into f by 4 into 4 into 4. Now here f is you number of computation reduces for the dimension f, and communication is same as what we had before, because so if I write down the equation here, you have a b comma d. You are for each device, this is for each device, f x y z, and you multiply here and you get b comma f x y z. So you get this sharded, and then you need to all gather this one. So if you have to all gather, then uh, uh, then as per the formula that we saw here, it is v by the bandwidth. So your total array size is 2bf, and this 2 comes from, sorry I forgot, this 2 comes from bf16. bf16 has 16 bits or 2 bytes, 2bf divided by w, or this is the sorry 3 into uh, w, and yeah, this is the bidirectional bandwidth. And these 3 again comes from the fact that we have sharded across 3 axes. So um, so we can see like these two are complementary to each other, where you have first you have sharded b, and in the second case you have sharded f instead. So let's go to the next type, where we have uh, some arrangement like this. The here b x y z is sharded, and we are gonna multiply with uh, matrix t x y z comma k. So here this contracting dimension is sharded, and um, for this we will be um, we have to for so if you remember, this was case um, 2, where one of our contracting dimension is being shard where sorry, this is case 3, where both of our contracting dimensions are being sharded. And to do this operation, uh, if you see here, the flops doesn't change, uh, other than here it will be 4 comma 4 comma 4 into f. So here the less amount of computations that you are paying is for this d dimension only. And if you come to comms now, so after you have done the so here, if you remember, uh, this question was part of derived from case 3, where both multiplicants have sharded contracting dimensions, and we saw that here we have sharded the contracting dimension in both of our matrices. And here we first do a local matrix multiplication, and then we do an all reduce on that. And as discussed here, all reduce is equal to reduce scatter plus all gather. So hence all reduce is twice as expensive as all gather. So here, whatever all gather price we paid earlier, we are just going to pay a price on 2 times the price of that. So it will be 2 into 2 into uh, bf by 3 into the bandwidth. So this 2 comes from all reduce is 2 times expensive as all gather. This 2 comes from bf16, and this is the total size of the array, total size of array. And this comes from the fact that we have 3 axes and we are doing them simultaneously, and this is your bandwidth. So you can see, like, for comms you are paying a lot of comms here, so this won't have good latency, um, as compared to the earlier two cases that I described, where you didn't have the sharded dimension, the contacting dimension being sharded. So, and the final one is simply you have every device has d comma f, and it's simply like the flops is 2bdf, and communication is 0 because you don't need to communicate, everything is fully replicated already, everything is fully replicated already. But for other cases that we saw, we needed to fully replicate it. So if I so I created a streamlit visualization for this. So the first case that we discussed is, here we have sharded one of the dimension, so we do the matrix multiplication and then we do a all gather on this axis to get the fully replicated, uh, fully replicated in all the devices. So the sorry the first one was, here we sharded this one, we did the same multiplication and then we did an all gather. So the second one we discussed, and the third one is, we have the case 3, that from our matrix multiplication we did a matrix multiplication, local matrix multiplication, and then we had to do an all reduce, because uh, this is a like a local copy, and we have to accumulate the results across all the devices and then do also then do an all gather. So we have to do an all reduce, which is twice as expensive. So this is not low latency, and this one is like every chip has is doing the same work, and you don't have any communication. So there is no price to pay for communication, and but it will be inefficient if your matrices are big and you cannot fit in a you cannot even do this setting if your matrices don't fit in a GPU. So yeah, this was about so if you look at some of if I take for TPU v5p architecture, you can see the comms for the first two cases where the non-sharding dimension was non-contacting dimensions were sharded, the comms is nearly similar, but here the comms is almost twice as expensive because of the all reduce. Okay, now we'll start with question number 6. Let's first read the question. Let's say we want to perform a ix, zy, zy, and zyk. So it is sharded across the contacting dimension, and then it's sharded here too. It's sharded here too, and we'll get the response ixk, and the response is also sharded TPU v4 4,4 architecture. What communication do we perform, and how much time is spent on communication versus computation? So let's first solve this question. So this question is saying that we have TPU v4 v5e architecture, where you have 4 comma 4, so you have two axes, and also like this architecture doesn't have wraparounds. So so to send data from here to here, uh, you cannot like send data like this, this is not allowed. So you have to send data from here, and to send data from here to here, at max it will take you 3 hops. So in worst case scenario, you will be paying a cost of 3 hops. uh, so for our strategies, we have two strategies, and this um, so here you can see that your these two dimensions, the contracting dimensions, are sharded, and also like this is sharded. But the good thing is that here it is we don't have to fully replicate it. We don't have to all gather the results here. So um, so the first method that we are going to do is uh, all gather and then matmul. So here we are going to all gather on the uh, uh, on the z, on this z axis. We are going to all gather here, and then we are going to do our matrix multiplication on each TPU. So let's first write down the shapes. You have ix, you have zy, and then zy comma k, and you get the results. You do matmul here, you get the results ix comma k. So if you check the tcoms here, so as I said, you have 3 hops here. So at worst case scenario, you will be uh, paying 3 hops. So you have 3 factor of 3 here, and then your I is sharded, your j is sharded, and your j is sharded. So you will be transferring this data across uh, the GPUs. um, First, because we'll be first doing an all gather on all the GPUs. So it will be your I is sharded and your j is sharded, and you need to multiply with 2 because this is BF16, and you are going to divide it by uh, the bandwidth, which is 4.5 e to the power 10. You can cross verify that from the TPU architecture. So this will be the bandwidth, and now uh, now this communication was for this matrix. Also we need to do communication for this matrix, and here G, only the G row is sharded. So again 3 hops, this is the hops. You need to have hops because you cannot do wraparounds. You need 3 hops. You have z by 4, and you have k, and you do 2 because this is BF16, and now then you will divide by w, which is 4.5 e to the power 10. So this is your bandwidth. So this is your total communication that you will be paying for uh, this um, uh, to first all gather the z, uh, all gather this contacting dimension across all the TPUs, and then simply your matmul would be uh, 2ijk, and here it will be by 4 because you have ix. So this is the total computation and communication you are going to do for uh, first scenario. And for the second, I'm gonna add a new page. So let's see what the second is. So our other strategy is um, so this is all from the case 2. in your matrix multiplication. If you go back to the previous video, you can learn about this more about this in the case 2. So here what you can do is you can matmul and then do reduce scatter, and you can do this because, let me write down the equations again. You have aix z comma zy matmul with b zy comma k comma k, and you get c ix comma k. So here it is ix. So uh, so you don't know full replication, so you are okay with having partial results in all your devices. So if you had to do replication, if you wanted to have ci comma k, then you needed to do an all reduce, which is twice as expensive as all gather. But reduce scatter is not twice as expensive because it's uh, um, it's the same formulation as all gather. um, it's the same formula as all gather. So here first you um, if you come to flops, you have 2 I by 4 and j by 4, you and then k, so it is 2 I j k by 16. So you are paying lot less on the flops, and this is because you have ix sharded and zy's also sharded, if you see here. And as we are first doing matmul, so we are doing matmul on smaller matrices, and after that you will be doing the reduce scatter. Now to do reduce scatter, you have again 3, which is the number of hops. Remember that you have a TPU v5p architecture which doesn't have wraparounds, so to send data from here to here you need to have 3 hops. And you have 3 hops, you have 2 which comes from bf16, and you have I by 4 because this is still sharded, and and uh, and you have 1 by 4 and k. So this comes from the fact that you also have uh, z sharded. So in reduce scatter you will be kind of gathering all the results from all the devices and then doing an operation and then just like relieving those uh, 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 gathered arrays, so you won't be keeping them. So you have to also gather the z partial results, and this divided by w, which is the bandwidth. So if I have to show you how the results look like, so you have 2 dimensions. Let me actually, like, let me show you by this. uh, yeah, so here you can see in the first strategy, if I'll increase the dimension. Yeah, you will here you have the first strategy that is described is you do an all gather and then you do an matmul. So you do an all gather across the chips. So if I go next, you do an all gather across the chips and then you do an matmul. So you will be paying a lot of so first you have to do communication and then computation. But if you but if you do um, this method where you first do an matmul, and you can see here it is an outer product. It is an outer product, and after you do this matmul, here I have done all reduce, but you don't need all reduce because uh, our matrix is already sharded here. We want sharded matrix. So if you want I here, then you do all reduce, but it is, as it is ix, you won't need to do all reduce. So you can just do reduce scatter and you can see like you have less number of flops to do, and also um, the communication also decreases because you are doing you have another extra factor here. So this is kind of preferred, and um, and so yeah, like both of them have their trade-offs on how they do the operations, and so it will depend on we if you compute these two things, and it will depend on I and j, and what's your bandwidth, and if you can do even do bidirectional. If you can do bidirectional, then these three drops off, which will be really helpful. So um, yeah, like it's a trade-off that you have to calculate and see, but yeah, this will be the formulation for both of those methods. um, so if I go back to question 6, so yeah, like you have these two, and and in in the question, if you have seen this part, so we answered this part. Now we need to answer this. uh, so the question is saying that what about if we have this, how can we do this operation? So if I come down here, so it is saying the first case is a I x comma z z matrix multiplies with z x comma k y. Let me just reconfirm a x z k y. Yes. So uh, so we have TPU v4 v5p architecture. It is 4 comma 4. um, so we have this architecture here, and so it's saying that how to do matrix multiplication for this. And in the question you can see that it is written that when we combine data tensor and zero sharding. We'll be discussing more about this in the next chapter, but I have also another video in my LLM lecture series which discusses about this. But the basic idea is generally your matrix. So this is your weight matrix. This is your weight matrix, and this is generally sharded across the devices. And because like you need to care about your activations, and you need to care about your weight matrices sizes, so all these things are sharded, and this ix is sharded for tensor parallelism, this ix. So so when you are training, you have this setting. So how can you do matrix multiplication so that you can get back this result? um, so if you look at this, so if you have to do this, so you have to all gather. So if I'll go back here, so if you look at this, this is z. So here you have to do an all gather here, all gather here, and then if you do an all gather here, so this is ix j, and you have to do an all gather here, this is j ky, and you get the result ix comma ky. So so the entire thing is you need to do an all gather followed by a matmul. That's what you have to do, all gather and then a matmul. um, so all gather, as we discussed here, TPU v4 v5p architecture has 3 hops. So this is the hops, and you have hops, and here you are gathering over the z axis, z only. Yeah, you are gathering over the z. uh, uh, so you are gathering over z axis, and you need to sorry, did I miss something? So you have only ZX here. So you need to only gather here. Do an all gather here. So you need to do an all gather on Z by 4, comma K by 4, because K is also sharded, divided by the bandwidth. So this is your um, this is your communication for doing an all gather. And for matmul it will be you have, so you have now, after doing an all gather, you have uh, I overwrote actually. So when you do an all gather here, you get J, and you need to do a matrix multiplication here. You can see I is sharded, K is sharded. So I is sharded and K is sharded and J is fully there. So it is 2IJK divided by 16. So this is the flops you play. So here it is flops and here it is comms. So this you have to do this operation to get results when you have this kind of sharding. First is you have to do an all gather and then matmul. So if you know about 0, then there you have to do an all gather and then do matrix multiplication. So this was about the training. And there was another question here, this one. If we have this setting where it is ix comma j and j comma ky, and it said that you use that during inference, and during inference you don't need to. So during inference there are no activations. Hence, if you can fit your weight matrix, so this is generally your weight matrix. This is your weight matrix. If you can fit this weight matrix, then you just like fit that matrix in your device. You don't need to shard it like here, what you had to do during training. But during training, we keep track of activations that are optimizer state. So it becomes super expensive. So you have to shard the weights. But in inference, you don't have to shard the weights. So this becomes really simple, where you are just doing the matrix multiplication, and there is there is no need to do any so it is only flops, and you don't need to communicate to because if you do this matrix multiplication, you will get cix comma ky. So yeah, so the total flops is basically for TPU v5p architecture is just t2 comma, so this comes from 2, the factor 2 comes from flops in matrix multiplication, 2I by 4 into j into k by 4. So you are just paying cost for the floating point operations, TPU v5 architecture. So this was all about question 6. Okay, now let's get started with the question number 7. The question is, a typical transform block has two matrices where F is much greater than D, and with a batch size of B, the whole block is C dot B dot X, and let's pick D equals this much, F is this much, B equal to 128, um, and assume everything is in B floor 16. Assume you are running on TPU v5 2, 2, 2 slice, but assume each TPU only has 300 MB of free memory. So we have only a TPU v5 E architecture which has T 2, 2, 0, 1, 0, 1. This is your device mesh. But assume each TPU only has 300 MB of free memory. How should B, C, and output be sharded to stay below the memory limit while minimizing overall time? how much time is spent on comps and flops. So we will follow the notion from the book, and the book suggests, for first let's calculate how much memory does each of our matrices consume. So we have two matrices, uh, this one and this one. So it is like, sorry, it is df and ft. uh, we have these two matrices, and so the total memory is 2 into um, uh, df, uh, 2 into df, and this comes around 536 megabytes. So we have a constraint of 300 megabytes of free memory in each GPU. So clearly we cannot keep these two weights in all our devices. So we need to short them. And if you also calculate the activations, the activations are much more lower. The activations are like your batch size, or like transformer, like what's coming in, it's batch size comma d. So this is your activations. So your activations is equal to 2. So this 2 comes from bf16 actually. So you have 2 into uh, 128 into 18192. It's like b and d, and this comes around 2 megabytes. So your activations is very small, but your weights are really huge. So an intuition says that you should try to try to uh, gather or do communication on the activations. So if you uh, try to have the entire weight matrix in one of the GPUs, then you will run out of memory. Uh, but if you try to do operation where you gather only the activations, then you won't have the problem to then you won't have the problem of gathering more than what is being prescribed here. So so you have an activations of b comma d. So you need to shard this. Let's see how you can shard this. You can either shard this by b d x y, and then you do matrix multiplication with the first matrix. First matrix is given by d comma f x y, and the second matrix is given by d comma fxy comma d. So yeah, I got this from the book, and the good thing here is, if you have to do this matrix multiplication, first you need to do an all gather on this axis, so that you have b comma d, and this is activation, so it's a small gather. As we discussed, it's just 2 megabytes, and then you multiply with d fxy, and you will get b comma fxy, and you have already this sharded, this is sharded, and you do this matrix multiplication to get b comma d, the matrix that you want the results out, b comma d. So transformer is a very homogeneous architecture, so whatever shape goes in also gets out. So yeah, we had an activation of b comma d, and now we are also sending back an activations b comma d. So uh, this kind of sharding is like really helpful, and you can do the all gather and then matrix multiplication. You do two matrix multiplications, and then you don't need to um, uh, accumulate the results, because these are um, these results are still uh, replicated across the GPUs. So you can choose to uh, short, but yeah, like it depends on. I don't think you'll be like running out of memory if you have this. So if we have this configuration, so uh, so this one, when you do an all gather, so this will be 2 megabytes per device, and you have f x comma y. So if you see here, f uh, is the biggest memory consuming thing here. Um, and so when you shard fxy, it means that you are sharding across two dimensions. So it's like by 2 by 2, so 3768 and it's 2 and 2, and this one comes around 8992 per device. And this is how you shard fx comma y in all the devices. uh, so yeah, I'll let you do the operation again, because I think we have been doing the same operations again and again. But yeah, like I got some hints from the book, and this pattern makes more sense, and this will be able to, without running out of memory, solve the question. So we will be skipping through question number 8, because this is mostly code. And in the Streamlit app, I have given some code snippet on different ways of doing all gather and all reduce. So yeah, feel free to look at it, and we'll not be spending a lot of time on the code, because uh, this lecture was mostly on getting our hands dirty with the questions, solving them by hand from scratch. So we'll be directly jumping to question number 3.9, uh, which is uh, which is uh, which is like really interesting. Um, so in case 2, we claim that when one input to a matml is sharded, this is the contacting dimension. We should all gather and perform the resulting contacting locally. Another strategy you might think is shard and then do an all reduce. So this is talking about the operations in case 2, where one of your contacting dimension was sharded. So if I have to show you the uh, diagram for this. So here you can see you have an all gather. So here, yeah, your one of the contacting dimension is sharded. So you first do an all gather, where you gather the A matrices across the chips or TPUs, and then you do the matrix multiplication, because you have fully replicated. Another option is you have your matrices like this, here and here, and this is going to do an outer product. So yeah, you do an outer product, and then you have to do an all reduce to get the results. uh, um, you have to get the results on all the GPUs to be same. And all reduce, but all reduce is twice as expensive as all gather, because all reduce is reduce scatter plus all gather. So um, here, this question is mainly asking about uh, which one would you prefer. And and the main caveat is, if you don't want you uh, things to be replicated, if you don't want things to be replicated, so which one would you prefer here? So we will first take, so we will have this matrices A n comma m and b m comma k, and these are sharded across different axes, and we will only be sharding this contacting dimensions. Keep a mind on that. So so we'll be sharding this contracting dimension, and we'll be sharding like this. So it is sharded here. um, um, so if you first do all gather, you will get the matrix A nm, and you did an all gather here nm, and then you do matrix multiplication b m comma k, and then you get the results a n comma k, right? So this is the operations that where you first do an all gather followed by the matrix multiplication, but you don't care about having all the results in one place. So uh, but by that I mean that you don't care about having fully n and k materialized in all the TPUs. So you can have it nx and uh, or kx. You can have them sharded and keep it in one of the GPUs. Um, so so if you don't care about having it fully replicated, so if you want to have fully replicated, then you have to do an all reduce, and we know that all reduce is reduce scatter plus all gather. So if you don't want fully replicated, then we only want this, and we don't want this. So we can only do reduce scatter, and which has the same cost as all gather, and we would be happy just doing that operations, and we'll be letting it go. uh, but the caveat here is that you will not have it fully replicated, and if we have to calculate uh, let's first do this in our method of uh, all gather and then doing matmul. So the first operation is you do all gather, then you do a matmul. So in all gather you have a uh, uh, communication of m here. So your mx is sharded, so you do an communication m, and so your total communication would be as we have discussed. Just a second. So you have n mx and j and k. So um so you will be doing communication on this axis, so which is on communication on this axis. So your nm um, would be communication, and the number of is the device specified across nd devices. uh, so I think there might be an issue here. This would be across the D devices. Okay, I was getting a little confused, but so in all gather, when you are doing all gather, so you are basically all doing an all gather on this matrix, and this matrix, the total length of this matrix is nm, and you might remember the formula that we have v by x, v by w, to be the total uh, total array size divided by the bandwidth. So if you remember, if I can go back here, here, so we derived this formula, so we'll be using this formula now. And so if you look at here the v, so this v is scales by nm, because this is the matrix that we are working on. So this scales by nm. So so your all gather or communication time scales by nm, and then you do the matmul, and also like you pay a lot of you pay cost for after you have doing all gather, it is nm, and come matmul with mk. So you pay the full cost of this matrix. So the second one is you do an matmul, but instead of all reduce, you just do a reduce scatter. So you have a n comma mx and b m comma k. So this sorry this gives you uh, a partial result of n uh, n comma k. So where you have a partial result and you need to do an all reduce here to get the full result, or you can, as we discussed here, you can just do a reduce scatter. If you do a reduce scatter, now you would have nx comma k. So instead of when you did all reduce, you would have the full matrix, but as you are doing reduce scatter, so you would only have nx comma k. So this so uh, we saw the reduce scatter and all gather have the same communication cost b by x. So this one would scale by nk. So you have nk and you have nm here. So um, so this one scales by if you take strategy 1, if you name this as strategy 1 and strategy 2. So strategy 1 by 2 is scales by m by k. So if your m is greater than k, so prefer doing the strategy 2 because then you will be paying less price. But if m is less than k, then prefer doing strategy 1 because here we'll be doing less communication. But also it depends on so here if you see um, in this operation you are paying less flops and you are just paying all of them in communication. But here you when you after you do an all gather, you have to pay the entire flop, and this flop would be 2nmk. But here it is lesser, it is 2n m by d k, because your m matrix is has been reduced. So you're just doing a partial result, you're getting a partial result. So this is the main conclusion, like based on the communication that we have. Okay, now the last question. uh, this is all-to-all communication pattern, and we discussed this deeply in the mixture of experts lecture, and we'll be discussing it more in upcoming lectures. But here we want to we want to find the communication cost of all-to-all. Let's first better understand all-to-all with this example here. Let me revert back. So you have in a device, you have all the data present. So you proceed one. So let's assume this is unidirectional. You can just send data in one way. So PCD is transferred. A doesn't need to be transferred. A stays here. Then here B is not transferred. B stays here. C and D are transferred. And then the next step is C stays here. D is only transferred. So in if I come back here, in all gathered we saw that suppose like you have four devices. So to transfer data from here to here, just assume that it is unidirectional. The data needs to go here, then here, then here. It all the data, every piece of data needs to travel through the entire device mesh to get to the other side. They cannot short circuit. uh, Everyone has to transfer at least d minus 1 hops. And uh, but in all to all we saw that if I go back to the streamlit application, like A didn't have to move, B only moved for once, C moved twice, and D moved once. So if you have like device of 4, so A moved only 0, B moved once, C moved twice, D moved thrice. So this is like 0 plus 1 plus 2 plus dot 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 d minus 1, which comes down to around d by d minus 2. So this is like the AP progression. So this comes around this much value. And here so the question is, you have a matrix of n cross n, so each one has a matrix n cross n, and you are transferring data uh, in all of this. So each one would have a shape of n square. Each of this device would have n square, n square, n square, n square, and you are transferring that data across d minus 1 hops. uh, you're transferring the data across d minus 1 hop. And uh, and okay, sorry, one thing I forgot to say was this one will be sharded, like this device is sharded here. So instead of it being n cross n, it is actually nx comma n. So this part is sharded. So uh, instead of being it n, it is actually I'll erase this. It is n by d into n, and we have d minus 1 hops. So it is n squared by d, d minus 1, or equal to n square 1 minus 1 by d. So if d is greater than 1, so this one is nearly n square. So this scales by the size of the matrix altogether that we discussed earlier. And the total comms time equal to n square by whatever bandwidth we have. But here if you can see, there is an extra factor 2 here. And so for particularly for all to all, you are transferring only this much amount of data. So this one will result to n square by d into uh, n square by d. And this one here also, one more thing that I forgot to mention is all of these matrices. So in mixture of experts or in all to all communications, all of these matrices are sharded n by d. All of these matrices are n by d comma n by d. All of these matrices are already sharded. So this one would be actually n square. So if I write it properly, it will be n by d, n by d into d, d minus 1 by 2. I got this only. So it cancels out n square by d, uh, 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 n square by 2, 1 by 1 minus d. So if you see all to all is n square by 2, and we had here n square. So all to all is around twice as less expensive, uh, uh, twice less expensive than all gather. So all to all has 2 times less cost. And in the questions earlier, like here, if you have, so we just discussed about bidirectional. If it is we just discussed about unidirectional, and if it is bidirectional, then the factor, then both of this factor would multiply by 2, and both of them would get faster. But the relative is always like all to all is two times less expensive, or like altogether is two times expensive for communication. This brings us into this lecture, and I hope this give you a idea about how I'm solving problems. If you have any queries, I'm one comment away. Thank you.